Good morning, students. In last class about structure of PCl3 and PCl5 explained. Okay, based on PCl3 and PCl5, phosphorus trichloride and phosphorus pentachloride. Last, one of the most important structure in a solid state, PCl5 exists in two complex ions. One is cationic, another one is anionic. In cationic state, phosphorus tetrachloride, that is tetrahedrally arranged. In anionic state, it exists as octahedral, PCl6 anionic. Based on this, in examination, they'll ask like, here PCl3 reacts with heavy water. Then what is the product obtained? Give reason. And what is the product obtained? Give corresponding formula. In first year, in hydrogen unit, heavy water we know. Water formula is we know, that is H2O. But here heavy water, that is DTO, deuterium oxide. Now, generally, here PCl3 reacts with water, H2O, it gives corresponding H3PO3 phosphorus acid plus here HCl is formed, hydrochloric acid. That is 3 Cls are there, that's why take 3 moles. Hydrogens 3 plus 3 6, that's why take here the 3 moles, balanced everything. Just like this, PCl3 react with heavy water, same here the PCl3 plus 3 moles of D2O, deuterium oxide. It gives here the D3 PO3 plus 3 DCl is formed. Similarly, here PCl5 react with H2O on hydrolysis. First it gives POCl3 plus HCl. Then it is again reacted with some excess amount of water, H2O. It gives here the H3PO4. Here phosphoric acid is formed. Plus again it is 3HCl is formed. Here the 3HCl is formed. Yesterday explained these reactions. Now similarly, here the PCl5 is reacted with heavy water, D2O, that is limited, not excess. Then it gives here the POCl3 plus here the DCl is formed. Here 2 are there, that's why take here the 2 DCl. This is the phosphorus oxychloride and deuterium chloride is formed. Very, very important reaction. With heavy water, just like water reactions only, instead of hydrogen, deuterium we can take. In unsaid textbook, in text like reactions given. Again here the PCl5 on heating at certain temperature, it gives phosphorus trichloride and chlorine gas is liberated. These are the some important points, extra points about PCl3 and PCl5. Clear? Then last, one of the most important concept is oxoacids of phosphorus. I'll discuss about oxoacids of phosphorus, very, very important. I'll create one important table based on they'll ask any one question either in a theory or in an objective. Oxoacids of phosphorus. Next important concept is oxoacids of phosphorus P. Here phosphorus forms many many oxoacids, they are like H3PO2, H3PO3, H4P2O5, H4P2O6, H3PO4, H4P2O7, and HPO3. These are the some important oxoacids of phosphorus. It forms variety oxoacids. One is H3PO2, H3PO3, H4P2O5, H4P2O6, H3PO4, H4P2O7, HPO3. So we'll discuss about all these oxoacids of phosphorus one by one. Okay? So here oxoacids of phosphorus are here. First one is H3PO2, H3PO3, or H4P2O7, H4P2O5. This is 6. H3PO4, H4P2O7. Finally, it is HPO3. These are the some important oxoacids of phosphorus. First one is about first oxoacids of phosphorus. That is, first column is name of oxoacid, name and its formula. Name and formula of oxoacid. Second one is oxidation state. Next one is structure of that oxoacid. Based on the structure, basicity of that oxoacid. Then simple preparation method. Simple preparation method. So these are the some important columns are the point about oxoacids. Here in this oxoacids, main important thing is basicity is important. That basicity is based on structure of that particular oxoacid. Preparation method. Now first one is here H3PO2. That H3PO2 name is your Hypo phosphorus acid. This hypophosphorus acid also called phosphoric acid. Its formula is H3PO2. It is. Its oxidation state is in this H3PO2. Oxygen is -2 into 2 -4. Yeah, +1 into 3. Compulsory, its oxidation state is +1. So in phosphorus, in hypophosphorus acid, phosphoric acid, phosphorus exhibit oxidation state is +1. This is one important column about hypophosphorus acid. Here oxidation state is here -1 oxidation -2 into 2 -4, compulsory +4 required complete. This is already +1 into 3 +3, and here only one phosphorus is there, +1. That's why oxidation state is 1. Its structure based on this Lewis dot structure. While writing the structure of this any oxoacids of phosphorus, one condition is there should be at least one P double bond O and one P bond OH. Compulsory. Setup like around phosphorus, compulsory one is P double bond O, remaining is POH. Then phosphorus, we know atomic number is, 15 electronic configuration, we know. Number of valence electrons, we know 5. Out of 5, these 2 electrons are bonded with oxygen first, that is P double bond O. Then remaining 3 are there. Out of these 3, one is bonded with oxygen. Condition this is, OH is compulsory, POH is compulsory. So the P double bond O and POH is compulsory. These 2 are common for all 6 or the 7 oxoacids of phosphorus. Now remaining 2 are there and hydrogen atoms 3 are there. 1 is here. That's why it is directly bonded with hydrogen. Like phosphorus is directly bonded with hydrogen. Here around phosphorus sigma bonds are 4 sigma bonds and 1 pi bond is there. That's why this phosphorus undergoes sp3 hybridization. Without any lone pair like lone pair, bond pair and bond pair, without any such a repulsive forces, sp3 means shows generally tetrahedral geometry. Bond angle is 109 degrees generally here, 28 minutes. In all these oxoacids, phosphorus undergoes same hybridization because around phosphorus 4 sigma covalent bonds are bonded. That's why it undergoes sp3 in all oxoacids. It undergoes compulsory sp3. Geometry is tetrahedral. So the basicity is one of the most important point. Basicity means your number of replaceable H atom hydrogen atoms. So how many hydrogen atoms are there means here total 3 hydrogen atoms are there. 1, 2, 3. Among all these 3 replaceable hydrogen atoms, only here 1, because directly bonded hydrogen atoms with phosphorus like these hydrogen atoms do not replace. Do not replace means in any orthophosphorus oxoacids of phosphorus, hydrogen atoms are directly bonded with phosphorus. They do not replace. Only one hydrogen atom only replaces. That's why your basicity is equals to 1. Then how to prepare this hypophosphorus acid? Nothing but balancing reactions, no need. Directly we can use the components here. White phosphorus. This is the white phosphorus. Reacted with the alkali solution. Alkali solution means we can use basic solution NaOH plus water, like, or BaOH taken twice, barium hydroxide plus water we can use. Then we'll get the corresponding H3PO2 preparation method. Balancing no need. Clear. What are the reagents we are using? What is the product obtained? Like this, in this we can manage, we can write all the remaining 6 oxoacids of phosphorus. Clear? One is like name and formula, oxidation state, structure and basicity and preparation method. Very, very important. Second one is H3PO3. It is called a orthophosphorus. Orthophosphorus. This is also called phosphonic. Not this is INIC or ONIC acid. It is. Formula is here H3PO3. This is. Its oxidation state is in this H3PO3. Now here the -2 into 3, -6, compulsory here, +6 required. Already hydrogen +3 is there. That's why phosphorus shows here the +3 oxidation state. Then its structure. Phosphorus acid or orthophosphorus acid structure. Now here there is only one phosphorus is there, it is. That's why P. Condition is there at least one P double bond O. That's why there is a P double bond O. And there is a one OH linkage. C. Remaining how many hydrogens and how many oxygen atoms. Already here two oxygen atoms completed. Again with this one hydrogen atom. Then here hydrogen. See here. 1, 2, 3 hydrogen atoms and 3 oxygen atom and 1 phosphorus is balanced. According to Lewis dot structure only. So first manage here P double bond O, one is one bond and here the POH linkage, remaining hydrogen and oxygen atoms balance it. So with two oxygen atoms, two hydrogen atoms are bonded, one is this. Directly bonded hydrogen atom cannot replace. Replaced hydrogen atoms are only here 2. That's why its basicity is equals to 2. It is a diabasic acid. It is a monobasic acid. First one is monobasic, it is the diabasic. So how to prepare this H3PO3? Nothing but here H3PO3. We know already PCl3. Hydrolysis of PCl3. Here the PCl3 is reacted with water, given already reaction. While explaining PCl3 structure, hydrolysis of PCl3 will get H3PO3. And also phosphorus trioxide like P4O6 react with water H2O also will get H3PO3. This is very important. Already these reactions discussed under PCl3 structure of PCl3 and properties of PCl3. So the second one is orthophosphorus acids. Then third one is here pyrophosphorus acid. Formula is here H4P2O5 it is. Pyrophosphorus. For this pyrophosphorus, here the two phosphorus atoms are there. That's why its oxidation state H4P2O5. In this -2 into 5 minus 10, here already +4 is there, +6 divided by 2, 2 oxygen atoms are there. That's why +6 by 2, that is +3 oxidation state here also. So it is hypo orthopyrophosphorus acid. Here two phosphorus and here oxygen atoms are 5 are there. So here once we can observe there is a phosphorus and oxygen double bond and phosphorus and OH is one compulsory. That's why here two phosphorus are there. Take care of the phosphorus, oxygen and phosphorus. Because it is odd number, managed like, then here oxygen containing 6 valence electrons, so 6, 2 are bonded with phosphorus. Then 4 oxygen atoms and 4 hydrogen atoms are there, managed like, yeah, there should be a compulsory double bond O and one is OH. Then yeah, there should be a double bond. Compulsory here again it is bond OH. Oxygen atoms are balanced here. Oxygen atoms are balanced. 1, 2, 3, 4, 5 are balanced. Now hydrogen atoms are only 2 are there. 1, 2 only. But around phosphorus 1, 2, 3 bonds only, sigma bonds, one more required. That's why it is with hydrogen and it is with hydrogen. These hydrogen atoms do not replace, only these hydrogen atoms are replaced. That's why your basicity also 2. That's why it is also a diabasic acid. Very, very important. That is pyrophosphorus acid, H4P2O5. Then your H4P2O5 is prepared by using same the obtained your H3PO3. That H3PO3 solution is reacted with the same PCl3, the same PCl3 combination. The above method only, PCl3, water and obtained H3PO3, we can react it on heating, will get H4P2O5. Very, very important method. Clear? Third one, about its oxidation state, then its structure, basicity, and preparation method. So the basicity just observed on the basis of its structure, not on the basis of number of hydrogen atoms. Here hydrogen atoms are 4 are there. Among all the 4, do not replace, because among these two hydrogen atoms are directly bonded with phosphorus. They do not replace. Only 2 hydrogen atoms are replaces. Then fourth one is here hypophosphoric acid. Phosphoric acid it is. Now up to here 3 are the lower oxidation states. This is hypo. First one again started hypo. That is H4P2O6 it is. In its oxidation state, H4P2O6, this is already 6 oxygen atoms are there, -2 into 6, -12 to balance that. Here already oxidation state +1 into 4. Again here 8 will get it 8 by 2, that is +4 oxidation state. Now once we can observe here oxygen atoms are base numbers are there. Phosphorus also this. That's why there is no phosphorus and oxygen linkage. Here we can take phosphorus and phosphorus linkage. So here the P double bond O is compulsory and one is OH group is compulsory. Write better you write on either side like this fast. Here the bond H. Remaining oxygen atoms 2 required and 2 hydrogen atoms are there. That's why again it is bonded with this. Again it is bonded with this. See here 1, 2, 3, 4 hydrogen atoms are replaces easily. Now oxygen atoms 1, 2, 3, 4, 5, 6, everything is balanced. And around each phosphorus 4 sigma bonds are there. They are tetrahedrally arranged. This tetrahedral and tetrahedral both are tetrahedral in nature. Same geometry, hybridization, bonding and everything. But in this case, hypophosphoric acid, in hypophosphoric acid, number of replaceable hydrogen atoms are how many are there? 4 are there. That's why your basicity is 4. It is a tetrabasic in nature. So here the just like hypophosphorus, we can use hypophosphoric, same combination. Here use white or the red phosphorus. Generally, yeah, the red phosphorus is strongly heated, generally less reactive than compared to white. Strongly heated with the alkali solution, it gives corresponding H4P2O6. Very, very important. So these are the 4 important oxoacids of phosphorus. Hypophosphorus, it is called a phosphonic. Like orthophosphorus, H3PO3, that is phosphonic. Names important. And pyrophosphorus acid, hypophosphoric acid. Formulas, oxidation states, structure, basicity, number of hydrogen atoms are replaced, and preparation method. Clear point? These are the 4 important. Remaining 3 are there, we'll discuss. Remaining 3 important structures. Last, I will remove this table. Okay, clear, completed, Nada? Noted? Orthophosphoric acid, H3PO4 it is. Its oxidation state is, in this case, H3PO4, in this case. Oxygen is minus 2 into 4, minus 8. Already it is plus 3, that's why it is plus 5. So oxidation state is plus 5. There is a condition around phosphorus, there should be a phosphorus and oxygen double bond. And here the phosphorus and hydroxy group 1 condition. Then in this H3PO4, 2 oxygen atoms completed, remaining 2 oxygen atoms are there with this oxygen, oxygen. Now remaining 2 hydrogen atoms are there, that's why it is bonded with hydrogen, So around phosphorus, directly OH group is linked, not hydrogen atoms. All the 3 hydrogen atoms are easily replaces. That's why here basicity is equals to 3. It is a triabasic acid. Now this H3PO4 is prepared by using here PCl5 with HCl. We'll get H2O. Already given here H3PO4 is prepared. Or P4O10 on hydrolysis will get this corresponding H3PO4. Already while explaining PCl5 preparation method and chemical properties explained hydrolysis. Here P4 like this. P4O10 is on hydrolysis, will get it. Are already prepared here the H3PO3 on heating gives here 3H3PO4 plus phosphine PH3 gas is liberated. Now here the disproportionation reaction takes place. Your oxidation state is plus 3 oxidation state, your oxidation state is plus 5, your oxidation state is minus 3. That's why this reaction is a disproportionation reaction. I'll explain that. So in this manner, we can prepare orthophosphoric acid. So different methods we can use to prepare this orthophosphoric acid. By using this number of replaceable hydrogen atoms, we'll get basicity, triabasic. And by using number of atoms present in the molecule, there is a condition to write its structure. One is phosphorus and oxygen double bond, and this one is compulsory. Remaining manganese based on their pentavalency. Yeah, around this sigma bonds are 4 and 1 is pi bond is present. Then last but one is sixth one is orthophosphoric. It is pyrophosphoric acid. Formula is H4P2O7. Now your oxidation state is for this H4 P2O7, here minus 2 into 7, 14 already here 4 plus 4 is there, 2 phosphorus plus 10, 1 phosphorus is plus 5 oxidation state. Here also number of oxygen atoms are here, base number is present, and phosphorus are here, 2 phosphorus atoms are present, and hydrogen atoms are 4 are there. By using that we can manage. There should be a phosphorus and oxygen, one important linkage. So are the phosphorus and oxygen, there is one link like phosphorus and phosphorus like. Remaining 6 are there. There should be a double bond one, and it is OH group. And here the double bond O, there should be one like this. Now here structure is here remaining 1, 2, 3 are there. 2 bonds required. That's why it is oxygen atoms 1, 2, 3, 4, 5 are there. Now it is like OH linkage 1, 2, 3, 4, and here bond OH linkage. So 1, 2, 3, 4, 5, 6, 7 are there. Now phosphorus 2 are there. Hydrogen atoms 4 are there. Yeah, replaceable hydrogen atoms are also here. 4 replaceable hydrogen atoms are there. So basicity is 4. It is the tetrabasic in nature. Basicity is 4. Now it is prepared by using by heating this obtained H3PO4 or heating on strong heating. We'll get like 2 moles if we can take care the H4 P2O7 plus H2O is formed on heating phosphoric acids. Then last one is one of the most important, that is metaphosphoric acids. Our 7th one is metaphosphoric. This metaphosphoric acid formula is HPO3 taken N. Here N indicates the number of this phosphoric metaphosphoric molecule. Here it forms 2 important groups. One is cyclic metaphosphoric acids, cyclic metaphosphoric, and polymeric metaphosphoric acids. I'll explain these 2 important structures, cyclic and metaphosphoric acids. Its basicity changes based on their number of these N molecules. And it is prepared by using dehydration of phosphorus acid. Here the phosphorus acid H3PO3 is reacted with Br2 also. We'll get here HPO3 plus 2HBr is formed. Or direct here the H3PO3 on dehydration will get HPO3 plus water, dehydration of this H3PO4 will get H2O like. These are the some important preparation methods for all the oxoacids of phosphorus. So here one of the most important structure is cyclic metaphosphoric acid and polymeric metaphosphoric acids. We'll create cyclic metaphosphoric and polymeric metaphosphoric acids. Okay, just observe it. 2 important structures. Then we'll discuss some important points about oxoacids of phosphorus. Then some additional important points about this oxides of phosphorus. No need to read for PU level or a theory path, for objective only. So here your HPO3, this is taken N, your polymeric. If you can take 3 moles, cyclic trimeric metaphosphoric. Many, if you can take many molecules we'll get a polymeric structures. Yeah, simply metaphosphoric acid, there should be a double bond O and bond OH condition. PO3 is there. This is linked with the other carbon atoms. These two are common. OH and P double bond O is common. Now this is connected with the other in a cyclic or in polymeric. So here one is cyclic metaphosphoric acid. In this cyclic metaphosphoric acids, better you take like 3 molecules like here phosphorus and here phosphorus. Yeah, there should be a double bond and OH take like first. And there should be a double bond and OH. There should be a double bond and OH is common. Then oxygen here oxygen and here oxygen, better you take. This oxygen atom is connected maybe with this phosphorus. This is ready to link with the other. Now this phosphorus is connected with this. This is ready to link with this. Now this phosphorus is linked with this. This is ready to connect with this. See here, same model here. HPO3, phosphorus, 3 oxygen atoms and 1 hydrogen atom. So this oxygen atom is ready to connect with the other ring. Now here one electron is present on oxygen and lone pair of electrons are there here. Now it is connected with this one metaphosphoric acid and is connected with another metaphosphoric acid and is connected with another metaphosphoric acid. It forms a cyclic metaphosphoric acid. One structure this is. Okay. Second one is polymeric. Yeah, polymeric metaphosphoric acid. In this polymeric metaphosphoric acid, cyclic link takes place. Now take as P double bond O and it is OH linkage and it is oxygen, or take as oxygen. Now here the phosphorus and double bond O bond OH and it is linkage takes place. Now it is phosphorus double bond O and here the OH, now linkage takes place and so on. Now it is connected with this, now it is connected with this, now it is connected with this and so on with this connected phosphorus and so on. Cyclic, this is the one molecule, this is the second molecule, this is the third molecule and so on. Take an N. That is polymeric metaphosphoric and cyclic metaphosphoric acids. Okay, these are some important points about oxoacids of phosphorus. In these oxoacids of phosphorus, one is most important point is H3PO2 acts as a strongest reducing agent. That reducing capacity based on number of hydrogen atoms bonded with phosphorus directly. And here the H3PO3 disproportionate is converted into phosphoric acid and phosphine. Means lower oxidation states, that is +3 oxidation state converted into higher oxidation state +5, and lower oxidation state is -3, disproportionate. So these 2 points we'll discuss. Then I'll give some additional important extra points. So here we know H3PO3. Here in this phosphorus oxidation state is +3. So are they +3 to higher oxidation state like +4 and +5, not +6, because maximum number of valence electrons are 5 only. and here +3 to lower oxidation state like +2, +1, -1, -2, -3, like that is 3 to higher oxidation state plus lower oxidation state. So are the +3 to higher oxidation state, that is a removal of electron, that is oxidation reaction takes place. It is reduction reaction takes place. That's why only one can dissociate, means can undergo both oxidation as well as a reduction reaction. That's why that reaction acts as a disproportionation reaction. Now here one example is here 4 moles of H3PO3 on disproportionation. Disproportionation it gives here 3H3PO4 plus phosphine gas PH3 is formed. Here oxidation state is -3 here +5. So here only one phosphorus, here to here +5 oxidation state, and here to here -3 oxidation state. This is a reduction reaction takes place. This oxidation reaction takes place. That's why it undergoes a disproportionation reaction. Now here the second one is here the H3PO2 acts as a strongest reducing agent Ra based on their number of hydrogen atoms, H atoms directly bonded with the phosphorus. Like phosphorus, there is a double bond. Like this is 2 hydrogen atoms are directly bonded. That's why acts as a reducing nature, acts as a strongest reducing in nature. That is your H3PO2 reduces solution. This is H2O. Reduces 4 moles of AgNO3 to silver Ag, 0 here +1 oxidation state. Then it gives corresponding your HNO3, 4HNO3 plus phosphoric acid is formed, H3PO4 is formed. These are the some important points about oxoacids of phosphorus. Then finally, remaining 10 minutes time is there. Finally, I'll explain additional information about 15th group elements, that is oxides of phosphorus. Little bit information I'll give about oxides of phosphorus. They won't ask in theory or a PU level, just they'll ask in only for objective. Structure based questions are very, very important. Okay. For objective purpose, like for CET or for NEET or for JEE, important, that is oxides of phosphorus. Yeah, phosphorus forms 3 types of oxides. 3 types of oxides. There are, one is phosphorus trioxide, phosphorus tetroxide, phosphorus pentoxide. These oxides are dimerizes. Trioxide formula is P2O3. Tetroxide is P2O4. Pentoxide is P2O5. It is. Dimerizes means it gives here P4O6, here the P4O8, and here P4O10. These are the 3 important oxides of phosphorus. Dimerizes they are. So among these three, just I'll give a clue about trioxides and pentoxides. They are very, very important. So here trioxides and pentoxides. Make like columns, two important columns, important points. Now in this case, trioxides and pentoxides preparation methods. Here it is P4O6 or take as P2O3. Here P2O5 or P4O10, that is. So here the first preparation method, simple preparation method is P4, it is white phosphorus, more reactive. That's why white phosphorus. Oxygen, that is a limited supply. Then it gives here the P2O5 or P2O3. If it is dimerized, we can take as P4O6. If it is, we can take as 1 mole, here 6 means 3 moles balanced. If it is phosphorus, white phosphorus, now it is react with oxygen, that is excess, we'll get P4O10. Now here take 5 moles, we'll get it. Then second one is dehydration. Dehydration of H3PO3. Then here H3PO3 on heating nearly around 600 degrees Celsius. Here will get here the 2 moles if you can take like P2O3 plus water will get it. Removal of water. Here also same thing. Here the dehydration of H3PO4, that is here H3PO4 on dehydration on heating will get P2O5 plus water will get it. Balancing afterwards. Now it is trioxide and it is pentoxides. Very, very important oxides. Main important is structure of a trioxide and structure of a pentoxide. Okay, we'll discuss about trioxides and pentoxide structures and important points about this. Just observe it. Here P4O6 and here P4O10 structures. Just observe it here. I'll take like phosphorus, here phosphorus, and it is phosphorus. 4 phosphorus atoms. And oxygen atoms here are oxygen, 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 and oxygen. First manage like in both the cases. Here on oxygen atom, totally are 6 valence electrons are there at 6. One is bonded with phosphorus, another one is with this. Clear. Similarly, here also, again here with this phosphorus and oxygen. Phosphorus and oxygen. Then with phosphorus and phosphorus, just arrange like this tetrahedrally structures like this, dotted lines. Only to get the tetrahedral shape, we can manage like this. Here also like this, tetrahedral shape. Center point, tetrahedral point. Now for this, one more oxygen atom required, that's why I take here oxygen, it is connected with this, it is connected. And here oxygen atom, this is bonded with this is bonded with this. Here, here, and here, like this. Now around phosphorus, 1, here 2, 3 sigma bonds, remaining 2 electrons are there, here present on phosphorus. Here also same here 2 electrons. Here also on phosphorus 2 electrons. Here also on phosphorus 2 electrons. and identify on each oxygen atom how many lone pairs are there here. This is very, very important. How many phosphorus and oxygen like linkages are present here? Very, very important. See here, phosphorus, oxygen, phosphorus linkages are here. Linkages are 6 are there. One of the most important points. 1, 2, 3, 4, 5, and it is 6 linkages. How many lone pairs are there means here are 2. Sorry, here are 2 lone pair. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total here the 16 lone pairs are there. Number of sigma bonds, observe here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sigma bonds are there. 12 sigma bonds. Like, identify each and every one point on the basis of these P4 O6. Similarly, P4 O10 also same. Only your oxygen atoms are increased 4. That's why these oxygen atoms are connected here 1, 2, 3, 4. Remaining everything is same. Okay, I will write, note down just. It is phosphorus, phosphorus, your phosphorus and phosphorus. Corners oxygen, oxygen, your oxygen atoms. Link up like this. Link up, then it is tetrahedrally dotted lines arranged like this, Now here one oxygen atom is bonded like this, here also an oxygen atom is bonded like this. Now here oxygen atoms are connected with this here. This is the extra only, that's all. Remaining everything is the same. Remaining everything is same. Now here phosphorus, oxygen, phosphorus, sigma bonds are 6 only. And here the lone pair of electrons are here, totally here 2 are there extra lone pairs. But here already managed. So on counting all these here lone pairs like this, here 2 lone pairs. Here a lone pair of electrons, count it all these lone pairs. We'll get 20 lone pair of electrons. Here the 20 LP pairs are lone pairs are present. Sigma bonds are here. One extra here, one sigma. Here sigma, sigma, sigma. Pi bonds are 4 pi bonds are there here. That's why here 16 sigma bonds and 4 pi bonds are there. They are P pi and D pi bonds. This is complete additional information about oxides of phosphorus, that is trioxides and pentoxides. Based on this structure, they will ask any one question in objective. Like in phosphorus trioxide, phosphorus pentoxide, how many POP sigma bonds, how many lone pairs, how many sigma, how many pi bonds are there in both the cases. It is the dehydration of orthophosphorus acid. It is dehydration of orthophosphoric acid. Okay, this is complete explanation about 15th group elements. Tomorrow we'll discuss, we'll start about 16th group sulfur, oxygen family, oxygen, sulfur and its compounds. So 15th group only somewhat big chapter it is. Remaining 16, 17 little bit same similar properties we'll discuss tomorrow. Okay, take care. Thank you.